Object's side is u1. Can you solve for v now? If you are getting v equal to -3, then it means it is the very same place. Exactly the same place. So you must make a note that real depth upon apparent depth formula or the shift formula, these formulae are applicable only for flat surface, not for the curved surface. You may have to check your workings. Yes, plus 30. It will be on the right side. If you would like this to be discussed on the board, raise your hand. R will be plus 5. Solve for V and see if you are getting plus 30 or not. It will be inverted image, but the size will be the same. The height will be the same, which is 0.5 mm. Any questions? Let me know. There will be two answers. First answer is -6. Yes, -6 mm. Second answer, okay, looks like you are still doing the second one. Yes, -5. But -5 is from a different point, I suppose. Yes. Left of second surface. So -5 is from here and -6 is from here. These are the answers. If you would like this to be discussed on the board, then raise your hand. In which part you have problem? First part, second part, or both? All right. So I assume that for the first part you are getting V equal to -6 mm. So that image will act as an object for the second part. This will be 6. This is how much? 2 plus 2, 4. 4 plus 6. So for this interface, U will be -10 mm. And rays are coming from where? Rays are coming from where for this interface? They are coming from optically rarer medium. So mu1 will be 1. Mu1 will be 1. This is air. Rays are coming from here. And that side is water. So mu2 will be 4 by 3. Then radius, this is on the left. So it means capital R would be -2. Just put these values and tell me if you do not get -5 mm for V from here. And any questions if you have, then let me know. Imagine these two surfaces and take this thickness to be very, very small. These two surfaces will have two radii. In this drawing, the center for this will be on the right side, C1, and center for this will be on the left side, C2. You may have a situation like this also. Now in this case, both C's are on the left side. You can have this type of situation also. Here for this surface, C1 is here. For this surface, C2 is here. Several possibilities are there. The line that you obtain by joining C1 and C2 is called the principal axis. And then this is the optical center. We normally ignore the thickness for such lenses. While we were careful in these situations, V's from here or V's from here, because we could not ignore the thickness. Here, it doesn't matter. We won't be saying from here, left side, or this right side, but we would just be saying optical center here. This is okay because thickness is small, but not okay if thickness is not small, in which case you must resort to this discussion. So thin lens is an approximation basically for thin cases only. Now there can be two radii of curvature, R1 and R2. They may be equal, they may not be equal. There are two foci also. We say second focus, first focus, or second focal length, first focal length. What do they mean? parallel rays where they meet, where parallel rays meet, that is second focus. In this drawing, it could look like this. So where parallel rays meet, that is the second focus. They meet or they appear to meet. In this case, they actually meet. And in this case, they appear to meet when extended. So you have parallel rays diverging, appear to meet. So that's about the second focus and second focal length. Second focal length means distance from optical center to that point. In this drawing, it would be something like this. In this drawing, it would be something like this. Then what about the first focal length? Imagine some object placed here and then rays becoming parallel. So where that object is placed, distance from the object to the optical center, that is called the first focal length. Now these things are for technical discussion, but most of the times practically you will see that the two C's are equal, two R's are equal, R1 is equal to R2. So the two C's become symmetrical, two focal lengths become equal. That's what happens in most cases. Sign convention, same. Cartesian sign convention we follow. X-axis minus x-axis, y-axis minus y-axis. Right? So very simple. We have been following it since curved mirrors, and we continue to do so. Just for the sake of practice, can you tell me what would be the sign for U, V, F, R1, R2? What I am referring to, small f here is the secondary focus. Second focal length. Second focal length. Let me also show one thing, that I is on the left side. And F2 is here. Now you should be able to give the complete answer. U is negative. Why is V positive? This is I. V should be negative. F is, why is F positive? F2 is here. F is negative. R1 and R2 both are on the right. Both are positive. U negative, V negative, F negative, R1 is plus, R2 is plus. Any questions? Let me know. First, there will be refraction from this surface. Let's say mu here is mu2, mu outside is mu1. Let's use one subscript for this side, this surface, two subscript for this surface. Now we are saying here that whatever is the sign of u, that will be retained. And this V for I dash is say V dash. So whatever sign is there, we will retain it and we will get some V dash from this formula. Whatever is the sign for R, that will be put up here. Depending on whatever case you have, both sides convex, both sides concave, whatever case you have, in this formula you will put the appropriate sign. So you will get V dash. Okay? So this will be the general form. It will be applicable to any case. Depending on the case, you will put the sign plus or minus for R. Yes, that should be R1. Now this I dash will act as object for this surface. Now rays are coming from mu2. This is mu1. Rays are coming from mu2. So that will be mu2. Now u is V dash with sign, of course. Sign is inside V dash. Mu2 final is mu1 in this case, and absolutely final V is V. Then they will interchange their positions. R2. Now R2 will come with sign depending on whatever case we are handling, both convex, both concave, or whatever. So this will be a general thing which will be valid. We don't want V dash. We would like to add these. So we would have on addition mu1 by V minus mu1 by U equal to mu2 minus mu1 1 upon R1 minus 1 upon R2. Right? Which I can write as this or this. Now note some points here. When we wrote the first equation, distances were measured from this point, P. When we wrote this, distances were measured from P dash. So when we said V dash, then V dash was actually Pi dash. But we said V dash would act as object for this surface, then technically the object distance should have been P dash I dash. But we still took it as Pi dash. So this is only good if lens is thin. Otherwise you must go back and use this type of thing. Fat lens. This is fat lens. So we have been making approximation already. Now, we have defined focus. That is, parallel rays come, they meet at a point, that focus, and we have focal length. So if I take limit u approaching infinity, then v will become f, 1 by infinity is 0, and I would have this. Most of the times, outside is air. In that case, if outside is air, mu1 is 1. I am writing mu2 as just mu. That is called lens maker's formula. So if your doctor tells you that you need this much focal length, and you take that prescription to some optician, then from this, that optician can calculate how that thing has to be made, how R1 and R2 can be chosen for some specific material Now that's length maker's formula. We can also arrive at length formula 1 upon v minus 1 upon u is something. 1 upon f is also that thing, isn't it? They are same. And that means 1 upon f is 1 upon v minus 1 upon u. This is called the length formula. Any questions? Let me know. Technically speaking, there are two refractions, one here and one there. So technically speaking, there should be one bending here, one more bending here. But often we don't show two bendings in thin lenses. Parallel ray goes through focus. The ray through the center goes straight. That's the property. Parallel ray goes through the focus. Ray going towards the center goes straight. Ray coming from the focus becomes parallel. All these are properties. Now in this case, two rays are shown and they are enough. They meet here. So you get the image of A at B. For O, you just need a straight ray. That's it, straight. Not that you cannot take other rays for O also. You can take as many rays for O as you want. O will have its image at this point, A will have its image at this point. That's the image. We want the formula for magnification. Magnification is defined as I by O. I with sign upon O with sign. Now I have used I and O here. I here is height, O here is height. Which sign? Let me delete I and O. Let's say this is AB, this is A dash B dash. That is P. Now while previous derivation was a very general derivation, in fact there was no need for me to show this type of lens. There was no need for me to show biconvex. The derivation at no point assumed biconvex or any other type. But here we will derive it for this drawing, but it works for other cases as well. But we derive it for this drawing. And for this drawing, I is plus A dash B dash. A dash B dash is a geometrical distance. It is positive always. Geometrical distance is always positive upon AB. So O is plus, AB is anyway plus, I is plus Y. So this is okay. Now this small triangle and that big triangle, they are both 90 degrees. Angles are same. So angle similarity, they are similar triangles. So we have A dash B dash upon AB equal to A dash P upon AP. But A dash P is minus V, AP is minus U. So V by U. V by U is the formula. Though we have derived it for this drawing, it works for all cases, for other types of lenses as well, and for this lens also, for different situations where AB is placed. Here AB is quite close to the lens, but even if it goes farther, this works. Any questions about lateral magnification results? If you have, then let me know. This is your assignment question. We stop now.